Question 2. Diamagnetism. We model a diamagnetic substance to have all atoms oriented so that the electron orbits are in XY plane, exactly half of which are clockwise and half counterclockwise when viewed from the positive x-axis looking toward the origin. Some substances are predominantly diamagnetic. So first question. Calculate the total magnetic moment of a diamagnetic substance with the n atoms. And write your answer in terms of any of all the next parameters. Charge of electron, mass of electron, radius of orbit, number of electrons, and magnetic permittivity. So if we have exactly half are going positive direction and half negative direction, so total magnetic momentum is 0. Next question. An external magnetic field B0 equal B0Z in Z direction is applied to the substance. Assume that the introduction of the external field doesn't change the fact that the electron moves in a circular orbit of radius r. Determine delta omega, the change in angular velocity of the electron for both the clockwise and counterclockwise orbits. Throughout this entire problem, you can assume that d omega much less than omega 0. And write your answer in terms of this only. So if we have orbit of electron and the magnetic field is going this way, it means that we have additional force from a magnetic field which is going either inside to the center of this orbit or outside. It depends which direction this electron rotates. And we can, from here we can write equation. So we have centripetal force ME R omega square equal E square over 4 pi epsilon 0 R square, and we have plus or minus, this is from proton force, and plus minus force from magnetic field R omega 0 B. So this is the expression for current. Okay, so now let's do some math. This was initial expression for initial omega 0, so we can replace it by ME R omega 0 square, and we can move this to the left. So we have mass of electron multiplied by radius and multiplied by omega, new omega square minus omega 0 square. That's equal plus minus E R omega 0 B. Now let's do things. So we have mass of electron, R is cancelled, and we have omega plus omega 0, and here we have omega minus omega 0, which we can write. This one is delta omega, and that's equal to E omega 0 B. So because omega very close to omega 0, we can replace it by 2 omega 0. So we have E 2 omega 0 d omega equal E, this is plus minus E omega 0 B. And finally we have this expression that d omega 0 equal plus minus E B 0 over 2 mass of electron. So that's the answer for part B. E B 0 over 2 m electron. Question C. Assume that the external field is turned on at a constant rate in a time interval delta t. That is to say, when t equals 0, the external field is 0, and then when time equals delta t, the external field is B0. Determine the induced EMF. Experienced by the electron. Write your answer in terms of any of following parameters, which are presented here. Also omega 0. So when we have orbit of electron for time delta t, it orbits n times, and if we increase magnetic field B by this rate, we can write that EMF equal negative delta F over delta T, where F is magnetic flux through this area covered by electron. But our electron for time delta t made n turns. It means that this EMF acting on electron n times. So we need to multiply this by n, this factor. And now let's count. What is it? We have n multiplied by area, which is pi r square, and multiplied by B0 over delta t. So we can move this delta t here, and that will be number of turn by time delta t. So that's n over delta t pi r square B0. And what is delta n over delta t? That's a number of turns for 1 second. So it means that n over delta t, that's just equal to omega 0 r over 2 pi r. So that's the speed of electron over distance, which is equal omega 0 over 2 pi. And this is what we can put here. So we have answer pi and pi cancelled, and we have 1/2 omega 0 b0 r square. So that's the answer. So EMF equal 1/2 omega 0 b0 r square. Question D. Verify that the change in the kinetic energy of the electron satisfy expression delta K equal E EMF. So EMF, a change of kinetic energy, dk, that's equal d 1/2 m electron multiplied by v square. So that's equal to 1/2 m electron r square d omega square. And d omega square approximately equal to 2 omega d omega. So we have m electron r square multiplied by omega and d omega, and which is equal, we know what is d omega, that's a plus minus this expression. So we have m electron r square omega multiplied by E b0 over 2 mass of electron. So that's a plus minus. Now what do we have? We have masses cancelled, and then we have plus minus charge of electron multiplied by 1/2 omega 0 b0 r square. But this is our EMF. So that's electron, charge of electron multiplied by EMF. So we just prove it. dk equal plus minus E EMF. So here we need to put plus minus. Question E. Determine the change in the total magnetic moment dm for the n atoms when the external field is applied, writing your answer in terms of these parameters. So we have for one electron we have change of momentum, that's equal, so change of momentum dm equal d 1/2 E omega 0 r over 2. So which is equal 1/2 E r d omega 0, which is equal omega 0 is change of omega 0 is this one, so that will be 1/2 ER multiplied by 1/2 EB0 over mass of electron, which is E square R square B0 over 4 mass of electron. And the total change of momentum for whole material, that's equal n multiplied by this number. So this is the answer. dm equal n E square R square B 0 over 4 ME. And the last question is F. Suppose that the uniform magnetic field used in the previous parts of this problem is replaced with a bar magnet. So we have electrons and we have a magnet like this one. This is like north, this is south, doesn't matter. Would the diamagnetic substance be attracted or repelled by the bar magnet? How does your answer show this? So if we move this magnet close to this substance, it will change magnetic flux, but which induced the EMF such way that it tried to compensate this change of magnetic flux. To compensate, we need to repel it. So that's the answer. If we move it forward, that will repel this diamagnetic substance due to Lenz's law.